Okay, so good evening. Tonight we are delighted to have Bob AK3Y talk to us about getting started with Arduino. So over to you, Bob.
Okay, good evening, Alex. Good evening, everybody. Let me see if I can share my screen properly here. Okay, everybody can see that okay? So what I'd like to do is give you a basic introduction to the Arduino, and it's the Arduino microcontroller and the family of products that come under that name. We're going to go through a description of this particular microprocessor and how it relates to ham radio, which is the point of this presentation. And what you're going to see is King Arduin there on the bottom of Italy 1,000 years ago had a major role, I mean an absolutely major role in the production of the Arduino microcontroller, and you'll see that on the next view graph. Next couple view graphs. So the outline of the talk is going to start off with what is an Arduino? What do we mean by a microcontroller? What are some of the popular configurations that the Arduino finds itself in? What can you purchase? What's available off the shelf? How is the architecture of that particular little processor made? What are its pinouts? How does it talk to the outside world? How do you talk to it? And we're going to talk about setting up the hardware. How do you put the hardware together initially? It's very simple. And how do you talk to this thing through a software interface? In particular, we'll talk about what's called the Arduino Integrated Development Environment, or IDE, as the mechanism by which the programmer can send information to the Arduino and also receive information back from the Arduino, and to just determine how well that the interface of the Arduino is working with the rest of the electronics associated with it. So in this talk, since it's a fairly limited duration, there's no way I'm going to get through programming, computer programming. I'm going to assume that people have a little knowledge of what's involved there, but there's a lot to be to learn there if you have not begun computer programming initially. But what's nice about the Arduino, and the important thing about the Arduino is that you don't need to get deeply involved in C or C++ to really create your first application, and we'll see that in a few minutes. The Arduino has a lot of interesting features. It has digital input outputs for control of devices. It has digital to analog converters for conversion of digital information on the Arduino itself to an analog interface, for example, for creating modulations, for whisper or FT8 or anything else. It also has the inverse, the analog to digital converters all built on. We'll talk a little bit about functions and libraries involved with the Arduino and how we can make use of that in building up our applications. And most importantly, we'll talk about the peripheral communications interfaces that the Arduino microprocessor has. How does it talk to the outside world? How do we connect it to other devices? What other devices are available? How do I make this thing tick, and how do I make it control some radio functions that we might have? So particularly, I'll look at some of the ham radio applications, and we'll go through a few of those in a little detail. Like I said, I'm not going to spend a lot of time on the code because you'll see pretty quickly that a lot can be done without a deep knowledge of C or C++. Probably most importantly, I'm going to give you some sources and texts and reference sites that will help you branch off from this simple introductory presentation to really become proficient at using the Arduino as a piece of equipment in your shack. Let's see if I can get this to turn to the next page. Let's see, why is it not doing that? There we go. So what is an Arduino? We're talking about microcontrollers. What is a microcontroller? Well, just like the name says, a microcontroller is something very, very small, usually in the form of a single chip or a chip set. In this case, it's a single integrated circuit called the Atmega 328P from MicroCHIP. And it can control things. What does that mean? I can send digital information out. I can receive digital information in, and that's it, period. That's all it does. It's not a smart computer like your PC computer. It's not a Macintosh or even a Raspberry Pi. It's limited in its ability to talk to the outside world, but it's an amazing microprocessor in the sense that there's a tremendous number of applications that can be done using just the very simple interfaces that exist that are built into the board. The Arduino was begun really as an educational project. There was a university consortium along with an industry group in Italy that wanted to come up with a means for teaching literally teenagers and younger adults how to use computers and how to build something using a microcontroller. So the problem, if you think about it with a microcontroller, is if I give you a microcontroller chip, the Atmega 328P, and I hand it to you, what do you do with it? Well, it's got to have a clock, it's got to have some digital I/O, it's got to have a power supply, it has to have some means of programming. I've got to somehow either talk to it by USB or some other serial interface. So I've got to build all those individual connections up. So what the folks at this consortium wanted to do is take care of all those things, build a single board. And you'll see, for example, let me see if I can get the cursor to work here. Get my pen. If you look at this little module here, this is the Arduino Nano, and you see in here is the microcontroller integrated circuit, and all the rest of it is peripheral information or peripheral circuitry that allows it to talk to the outside world. It has a USB interface, it has a serial programming interface, it has a number of digital ports, a number of analog ports, it has a crystal oscillator, which is on the other side, it has a reset button, et cetera, et cetera. It's got a bunch of LEDs. Lots of things are built onto that individual circuit board so that you don't have to worry about making all those connections yourself. And I promised you I'd show you why the King Arduino was important. This project came about because the founders had a favorite bar in Ivrea, Italy. And it was named Arduino after King Arduino. And so as they started drinking more and more beer and more wine, I guess, it became a project that took off, and they attributed all this to King Arduino, and thus the name Arduino in what we see today. Okay, so there are a number of different Arduino boards. And I don't want to belabor this chart too much, but I just want to let you know that there are three main ones that most people seem to use. One is the Arduino Uno, which is, as you can see from the physical size, it's about 2.8 inches by about 2 inches, a fairly small board. There's the Arduino Nano, which was a little one I just showed you, and that's about 0.7 inches by about 1.8 inches. And then there's the Mega, which is about 4 inches by 2 inches. So they're all very tiny boards, but they have varying capacities. The Arduino Nano we're going to talk about primarily today because it's very inexpensive and it's very easy to use. It also is one that can be embedded very nicely into other projects, whereas the other ones are fairly bulky to embed in other projects. Again, I'm not going to belabor this much, but I want to show you what's on one of those boards. So in order to get a processor to work so that you don't have to muck around with all the digital interfaces and stuff, you start off with your microcontroller. This is the chip, the 328P from MicroCHIP. And of course, it needs to get started, it needs an oscillator. So that clock oscillator is on board. It has things such as a reset button, which is nice to have. It also has a small LED that's attached to pin 13, which we'll see that's important in a little bit. It tells you whether the board is working and also whether it's accepting data or not accepting data. It has a 5-volt regulated supply built in. The chip itself provides 3.3 volts out. So this particular board is able to handle both 5-volt and 3.3 volt logic. The other thing that's nice is has a USB chip that's built on. This is the FT232. There are other chips available. I'll talk about that a little bit later. And it has an integrated serial programming port, which allows you to talk to the Arduino directly as opposed to going through the USB port. This up here on the upper right-hand corner is simply the pinout. So there's a header that is on the board that allows you to connect inputs and outputs to it. Here's what the Arduino Nano looks like as a physical entity. And again, you see the Arduino 328, or the Atmega, I should say, 328 chip in the center. It's this little device here. The analog outputs are all along one side. The digital outputs are primarily along the other side, although there's another one that pops, pin 13 is over here. But most of the analog and digital interfaces are along the sides. And you talk to this through the mini USB port, which allows you to program it, and you're in business. So we'll show you how to do that in a bit. What's nice is that it has integrated serial interfaces, and those are these two pins over here that allow you to talk to the outside world through a simple serial interface. The digital pins are kind of interesting for a couple of reasons. One is, aside from just providing a logic high or a logic low, so for example, if you want to turn on a relay or turn on, let's say, a rotator that you're using for satellite communications or whatever, and you need to send it a logic high to say, let's start moving to the right. That's one thing it can do, but the digital pins also, several of them are allowed to be pulse width modulated. In other words, you can send a number to it, and that number then is converted into a pulse width modulated signal whose duty cycle is proportional to that number. And we'll see why that's important, because you can generate analog waveforms that way very easily. Okay, let's get started. How do we start building these things? What do we do to get it hooked up and running? Well, normally when you buy an Arduino, you get a package of parts, and this is typically what comes in the mail. This one I actually picked up from an eBayer in China. Why I went to China for this? Well, a couple reasons. One is, if you want to buy one new locally here, the Micro Center has them. They're about $20 a piece, which is relatively expensive for a little microcontroller, not too bad. But you can get these for about $4 or less in bulk from overseas. Now, are you getting a fake? Well, it turns out that the Arduino, if you remember, this was a project that was created by the Italians in 2005. The first thing they did when they created this project, it was they made it open source. So in other words, all the schematics, all the interfaces, even the software is all open source. So if you wanted to create your own Arduino microcontroller on a board and sell it, you're perfectly welcome to do so. So that wasn't the issue. The real problem became with the little USB chip. There's an FT232, which on the original Italian Arduinos was being used for the USB interface. On the clones, particularly the Chinese clones, they use a different type of serial interface. It's a different chip, which requires a different serial driver. Not a big deal, but you need to be aware of that when you're programming it. So what comes is a set of headers, and there are 3 headers here. This one here in the center, we usually typically don't use. There's no real need to connect that particular header. That's for in-circuit programming. It's all the programming that we're going to do on the Arduino can be done through the USB interface. So to start it off, the simplest way to put one of these together is to basically put these headers into a breadboard so that they stand up vertically. The problem with putting these things in by hand and holding them in your hand is that they wobble all over the place. So if you put the header pins in a standard breadboard and pop the Arduino on top, then it's very easy to solder these in a row, and that'll give you a nice straight configuration. Once you've got that soldered, there are 15 pins on each side. Then the next step is to apply power by putting a USB interface to it. It'll take 5 volts here. It'll also, by the way, there's a 5-volt pin if you look real carefully, of course, I just obliterated it there, but there's a 5-volt pin on the Arduino as well. So if I want to, I can actually put 5 volts in this way and not go through the USB interface. And that becomes important when I'm embedding this microcontroller in another project. I don't necessarily want to control it by USB or power it by USB. I may have a 12-volt supply that's already built in. I just put a 5-volt regulator chip in there and I'm up and running. So when I apply power to the Arduino, a couple things happen. One is the power light comes on, hopefully, and that means you've wired it at least partially correctly. But what also happens is pin 13, if you remember, was connected to an LED. One of these LEDs, which is this one here, is connected to pin 13, and it starts flashing. Flashes once a second. Now, why does it do that? Well, because inside the Arduinos, when they're supplied, they can be supplied with a boot algorithm, which essentially allows you to boot the Arduino from a 5-volt supply and get it up and running. And it has a program already built in called Blink. And the blink routine, which is a default program in all the Arduinos that are out there, just blinks the LED light 13 once a second. And once you've done that, you know that you've wired it correctly because the microprocessor has now been checked out, at least is working. You may have a bad solder joint maybe to a digital pin, which you'll find out later, but at least you know that you've got power going to the microcontroller and the microcontroller is talking back to you. Okay, that's part A. We've got the hardware built. How do we get software? How do we talk to this thing? And what do we do to talk to it? Well, there is a website, arduino.cc. And in arduino.cc, there are links to various versions of the Arduino IDE. So the integrated development environment for the Arduino is what's used to program this chip. And it's done only through the USB port on your computer. So you can do it under Windows, under Macintosh operating system, you can do it under Linux. I run it under Raspbian on the Raspberry Pi, which is a Linux variant. Lots of ways of running this thing. And it's very simple. You download it. Once you've downloaded it, you unzip it. It comes in zip format. I think the Mac does that automatically. Windows, you may need to unzip it. And once it's unzipped, then the first thing that happens when you run it is a sketch shows up. A sketch is a blank, right now it's a blank sketch, I should say, is a place where you place your code. And the sketch essentially has some interesting features to it. The first thing is it sets it up automatically to have two sort of function calls in it. One is called setup and one is called loop. The setup routine is executed once at the beginning when the power comes onto the Arduino. Whatever you put inside this section right here is executed once, and that's it. That's the last you'll ever see of it. The next step is the loop. Every single line of code that you place in here is executed in order and then repeated and repeated and repeated until either the Arduino burns out or you turn it off. So that goes forever, and you'll see how that makes programming very, very easy to do. Okay. Now, I mentioned that there are a couple different clones out there that exist of the Arduino because it was an open source architecture. So the chipset that comes with the Italian version, if you buy them directly from arduino.cc, and I believe also from Adafruit, you'll find that it has the FTDI chipset inside, which is the FT232 chipset that talks to the USB port. That requires the FTDI software driver, and there's the URL for that. By the way, I'll have this whole presentation on my website with a link at the end of the presentation, so you can have access to all this as well. Most of the clones use what's called a CH340G chipset, and that requires a slightly different, well, actually a very different serial driver. So as long as you know which serial driver you need to run, based on looking at the board itself, you'll see directly on the board whether it has an FTDI chip or a CH340 USB chip on it. You install the proper driver, and once you've installed the proper driver, the next thing to do is connect the Arduino to your PC USB port. Once you do that, you'll notice that inside the Arduino IDE, there's a box, or I should say a menu item called Tools. The Tools has 4 sections, or actually 3 important sections right down here. The 4th one is just getting board information, but the 3 important sections are selecting the board. So for example, in this case, we have an Arduino Nano. So I click and set up Arduino Nano. You can see there's a whole family of different Arduinos here that exist. The question is which one you make sure you select the correct one. There's also another set of Arduino's clone or Arduino compatibles, and I'll talk about that a little bit later. And that requires a slightly different interface, but very similar. The other thing is to set up the processor, and the processor in this case, I usually set it to Atmega 328P. Old bootloader. For a lot of the Chinese clones, the old bootloader works, whereas the normal one will work on the FTDI clones, so FTDI chips. So you need to play with that a little bit. If it doesn't talk to your Arduino, you've got the wrong processor listed. And finally, it's necessary to pick the port so that you know where the USB is talking to. In this case, it usually shows up as a serial port. This time it's a 1240. Serial interface, and that's where my board is located. So again, it's very simple. Set the construct the hardware, solder up the header pins, plug in the USB port, plug in a USB cable to the chip, and make sure it starts blinking. That tells you that the hardware is working properly. Put the USB cable to your computer, download the software. Select the correct chipset for the USB interface so your computer will talk to it, and then set up these 3 parameters here, and you're up and running. So the next step is to figure out what can we possibly do with this thing. Okay, so once I'm inside a sketch, I can now write my code, and typically the code is written in C or C++. Normally it's C inside here and C++ in what's some of the libraries. We'll talk about libraries later. But if you have some knowledge of C, that's great. You don't necessarily need that. You'll see that in a second here. This is really not much of a C programming language here that you see, but it can already do some interesting things. So in this case, I'm going to basically connect an external LED light. This could be also an external transistor switch. It could be an external relay through a transistor driver, anything that would accept a digital input output. What I'm going to do is with a digital control, I'm going to turn this LED on and turn it off in some fashion. I'm going to basically mimic what pin 13 did when I booted the microprocessor for the very first time. So the first thing I'm going to do is in the setup routines, I'm going to make some definitions. Actually, prior to that, I'm going to define a pin number 9. So we're going to set my LED so that it's going to be connected to pin number 9. If you look here, there's a digital pin 9. And I have my LED connected through a resistor. Goes through the LED and then comes back to the ground. So all I'm doing is essentially allowing pin D9 to pull up 5 volts on that resistor that connected to the LED and pull it down to 0. And if I can control it, I should be able to turn the LED on and off. Now, why did I put a resistor in there? Well, the Arduino by itself can sink about 40 milliamps of current. So if I can normally I'd be okay with a direct connection with one LED, but as soon as I put more than one or I connect it to something else, I can't, for example, connect it to a relay, because if I'm drawing a couple hundred milliamps, I will either burn out the Arduino or just essentially shut it down because it can't control it. So in order to do that, I have to be careful how much current I sink. And if I'm going to drive any kind of load, particularly an inductive load, I may want to have, I think I do want to have a transistor driver that interfaces between the Arduino and that particular load. So in the Arduino sketch, and sketch is just a computer program, first thing I do is I define my LED as being connected to pin 9. So I send up an integer, which is I define to be LED pin, and that could be called anything. It could be called Bob or George or whatever, but it's in this case, I define it as something I can recognize. I set it to pin 9. And in my setup, which is going to be executed once, I define that pin. And pin mode is a particular built-in program which allows me to select a pin, usually a digital pin, or it could be an analog pin as well. But in this case, it's a digital pin. And I set that pin to be an output. And what that allows it to do is the microcontroller now knows that when it gets a command to that LED pin, it sets its output either high or low, depending upon how it's commanded. So inside the loop, we're going to do exactly that. We're going to set up a loop which consists of turning the LED on and then turning it back off again. To turn the LED on, since it's a digital interface, I'm going to just use the command digital write. Very, very simple. I select the pin it's associated with. I could have multiple pins connected, for example. I could have LEDs on pins 4, 5, 6, 7, 8, 9, and 10. And the LED pin tells me which one to set a high to. That sets it to the high state, which usually is a few hundred millivolts below the VCC, in this case, 5 volts. And I delay 1000, another built-in command, delay 1000, it's 1000 milliseconds. And so that's 1 second. And then after I've delayed 1000 milliseconds, I'll set a digital write to low, and that turns the LED off by setting the voltage to 0 on that pin. I wait 1000 milliseconds, and then I just repeat this again. So I got to turn it back on again, turn it off, turn it back on, turn it back off. And what you'll see in a second, I hope, is the code running. And you can see that up in the upper right-hand corner, you'll see the LED now flashing up and down with that particular code stream. Okay, so this is the very simplest part of the Arduino. It allows me through all these digital interfaces, D1 to actually D0 through D13, I can use those for logic highs, logic lows. Give me lots of things I can program to control different functions. I want to control a TR switch. I want to control a relay that's connected to a filter that's used for sideband on 40 meters, and then I want to connect it to another one that's connected to 80 meters. That could all be done through these digital interface pins. And if you look at the bit 40, which was the Indian QRP rig, you'll see that the Arduino is used for exactly those purposes as well. Okay, let's now look at the next aspect of the Arduino. We've talked about digital output. Let's talk about analog output. And this is can also be done using the same digital pins. What we're going to do here is we're going to use the exact same pin, LED pin 9, as before. Well, again, as before, set it to be an output. And that's done once in the setup routine. So this is executed again only once, and it's never done again. And then inside the loop, I'm going to add my code. Now, I highly recommend that you put comments in all your code. So comments can be started with a // or it could be started with a */, finished with a star, with a /*, finished with a //. A few different ways of putting your comments in, and that's typical C structures. We'll go online now with your gift of 19. Okay. So what we're going to do now is I need an integer that is going to keep count for me. I want to start cycling this LED light brighter and brighter and brighter, turn it off, cycle it brighter and brighter and brighter, turn it off, and continue doing that. So what I'm going to do is I'm going to set up a counting integer I, and then for I equals 0 to 255, so I got 256 states. Remember, there are 256 outputs for the digital to analog conversion. Then I'm going to write, in this case, note that instead of digital write, I'm going to use an analog write, because I obliterated it there. Not very good at my, let's see, I should be able to erase that. There we go. So instead of a digital write, I'm going to do an analog write, and I'm going to analog write the number between 0 and 255 to the LED pin, and then I'm going to delay 20 milliseconds. Okay, so what am I doing? The digital pins and certain ones of them, not all of them, but several ones of them. And it depends on the version of the Arduino. The Arduino Nano, for example, can output on certain pins. For example, pins 5 and 6 will operate at 980 cycles. The other pins will operate on 490 cycles. And that's the rep rate of the pulse width modulated signal. An analog write sends a 0% duty cycle to that pin. An analog write of 0, I should say, sends a 0% duty cycle. An analog write of 255 sends a 100% duty cycle. So let's take a look at, this is looking at pin 9. This drawing right here is from oscilloscope drawing. And if you watch, you can see that I'm cycling through the numbers. There's 0. Now it's going up, it's creeping up to 255. Let's try that again. Oops. There we go. So it's starting at 0, and then it starts creeping up to 255. I truncated it here, but it'll continue to go ad nauseum until you tell it to stop. And so what that allows you to do is, because the cycle rate is fairly fast, nearly a kilohertz or half a kilohertz, the LED can't respond at that rate. And so what's going to happen is, if you look at the LED, you can see that the LED is now flashing brighter and brighter and brighter and brighter. Then it suddenly goes back to 0 and starts flashing up and up and up. Now notice you can't see it very well when it gets high, because the human eye is got a very logarithmic response to it. And so unless I did this logarithmically, you wouldn't see the fine gradations between, let's say, 210 and 215, for example. They would all look pretty much full brightness to you. Okay, so this is one way of now providing an analog output through an 8-bit D to A converter using the exact same structures we had before. Okay, now there's also the other way of connecting an analog device and creating a digital word out of it. So here's an example of an interesting connection to a potentiometer. What I've done is connected a simple 1K pot. I think it's 1K, it might be 20K, but it doesn't really matter as long as it's not drawing more than 40 milliamps. And I've connected it so that the center pin is connected to pin A0. And one side is connected to ground, and the other side of the potentiometer is connected to 5 volts. So 5 volts connected to the top side, 0 is connected to the bottom side, and the the wiper arm is connected to pin A0. And I'm going to call this an analog pin A0, and I'm going to set the value initially to 0. So in my setup, I want to take a look at what happens when I change that potentiometer. Well, by changing the potentiometer, and since I'm connected across a 5-volt supply, what I'm doing is changing the voltage going into pin A0. So I want to use the fact that pin A0 got connected to an analog to digital converter that provides numbers between 0 and 1023. So it's a 10-bit A to D converter that's built into the chip. And the way I do that is first of all, I define an analog pin to be an input now instead of an output. And I'll come back to serial in just a second. And inside my loop, I'm going to say, okay, let's, instead of writing to that pin, let's read from that pin. So I'm going to take the value as being the read value of the analog pin. So I'm going to say analog read, analog pin, and then I'm going to write that value out. Now, I didn't do this in live streaming here because it's really boring to watch me turn a potentiometer, but you'll see a bunch of numbers come out between 0 and 1023. Now, what am I seeing here? Where did this screen come from? The one that's writing all these numbers. Well, if you remember, inside the Arduino, there were a couple pins I referenced before that basically are connected to a serial interface. So inside the Arduino IDE, there is a ability to turn on a serial port, which can display anything that you would decide to write to it. So there is a function called serial that's already built into the Arduino. And in order to get that to work, I first, in my setup, I set the baud rate by saying serial.baud. dot begin 19,200, making sure that my baud rate on this particular screen is 19,200. By the way, I get that by connecting to I gotta move this over here to let's see, I get this. I got everybody's picture over my little drawing here. So let me move you guys out of the way. So there's a little button on the top right here. And if you click on that button, this screen appears. And that screen allows you to write data to it. And so this is extremely good for debugging purposes. So what I'm going to do is I set up a serial interface by saying serial.begin at 19,200, matching the baud rate of this screen to the baud rate I select in my Arduino. And then I say serial.print or serial.println, which means set a new line, the value of the analog read that I got from this instruction here. So what this does is continually read the value of the potentiometer voltage as a function of time. Now, a couple things that are important. If you know a little bit about C++, you'll realize that this is a C++ command. That serial is actually what's called a class, and .print or .println is what's called a method. Not important. What's important is that you know that there's a function call in C. It's really a function call that's called println, and that allows you to print the value out. And you have to preface it by the serial interface, which it basically is the data structure which creates this this screen. So that data structure creates this background screen, and from that background screen, you can write to it the data that you would like to look at inside your code. This will probably be one of your most important function calls as you start to write Arduino programming code. Serial.print, you'll find them all over the place as you try to debug what's going on. Okay, now this looks a little bit more complicated, but it really is not. It's putting together the things we just learned. So what I'm going to do is I'm going to use that same pin 9. I could have picked another pin just for grins, but I didn't. So I'm going to set a speaker pin now to pin 9. And I'm going to select the words per minute of, this is going to be a CW generator. And what I'm going to do is I'm going to set words per minute to 20 words per minute. I'm going to set up a timer interval because Morse code is all based on the relative times between a dot and a dash. I'm going to set a speaker volume. I can remember that's a pulse width modulated output. So I can set the value to be anywhere from 0 to 255. That's the duty cycle of the pulse width modulated waveform, which if I just apply it to a speaker will be proportional to the speaker volume. So if I make it 255, I'm going to get a really loud speaker volume. If I put it to 0, I get nothing out. Okay, and as before, I want that to be an output, so I set the speaker pin to output inside my setup command. Now here's where I do a little bit of math, very, very little bit of math, and this has to do with Morse code, how Morse code is developed. So the unit of time in Morse code is usually 1200 divided by the words per minute. So and that's in milliseconds. So the basic unit, that's a single dot of transmission, is 1200 milliseconds divided by the words per minute. So if I was operating at 20 words per minute, that would be 60 milliseconds, would be the equivalent length of a single dot. A dash is actually 3 times longer than that. So it's a dot times 3. A space is 3 times that. And a word space is 7 times that. So everything in Morse code is based on that single entity, which is proportional to the reciprocal of the words per minute. And that's this little equation here. Notice that we can do mathematics in here. In fact, you can do floating point mathematics. This is not a great floating point processor, so don't expect miracles out of it. It's a very simple microcontroller. But if I wanted to put 3.14159 in there and multiply by 2, there's no problem doing it. Just don't expect it to be doing that at 100 MIPS per second. You know, it's very slow. So now here, we're going to create a couple of functions. Remember that the print command was a function call. Well, I'm going to write my own functions here. Setup was a function. Let me get rid of some of this writing here. Setup was a function. loop was a function, and I'm going to create some other functions. I'm going to create a DA function. And what is a DA function? Well, it's going to create a output voltage that is setting the speaker pin, which is pin 9, to the speaker volume. So in other words, set it to a value of 100 in this case. I could set it to anything I want, but I'm going to set it to 100 up to 255. So I'm going to analog write a value of 100 to that. And while I'm writing that, remember that this is pulse width modulating. So it's generating a waveform that looks like this continually until I tell it not to do anything. So it's sending a very coarse square wave, sort of a lopsided square wave, because a duty cycle is proportional to that number I send, but it's sending a square wave to the speaker. I'm going to delay that. Before I do anything else, I'm going to delay by 3 times the basic unit. So in other words, I'm going to send that high signal to my speaker for a length of time equal to 3 dot periods, which is equivalent to 1 dash. Then I'm going to write a 0 and set it to delay time to be a single dot. So in other words, the delay between the next symbol or the next character, or the next symbol, because I haven't created a character yet, I've just created dot and dash, is going to be 1 time unit. Okay. Now the DIT is done the same way, only the DIT, remember, was only a single unit. So instead of using 3 of those, like I had here, I'm only going to do a single unit here, and that will set up a DIT. So I've got a dash, I've got a DIT, and now I have a space, which is just a delay of 3 units. I'm not sending anything to the speaker. I've got a word space, which is 7 units, and I'm not sending, again, anything to there. And now I'm going to create another function called CQ. Okay, well, I've got all these other functions here. I've got DIT and DA and spaces and what have you. So I'm going to create a CQ. My CQ is DA, DIT, with a space between that, which is the letter space. Remember, I just created a single letter C, so I got to put a letter space there. Then I got da, which is a Q, and I put a word space because the next thing would be the next word. So CQ is an entire word. From is DIT, or DE. So DIT with a space at the end, which is a letter space because that's a single letter, the letter D. And then I'm going to send DIT, which is the letter E. So I got DIT, which is D, DIT, which is E, and then I put a word space. So now this is DE, and this was CQ. So far so good. We're getting there. Next thing is, and of course I just wrote over it, but the next thing is my call sign. Let me get rid of this. I'm right up. What did I just do? Here we go. So my call sign is da, which is A space, da, K space, et cetera, and I put a space word at the end. And then in my loop command, I'm going to send this over and over and over again. I'm going to send CQ, CQ, CQ from AK3Y, AK3Y, AK3Y. I'm going to wait 10 units of time, and then I'm going to send it over and over again. And so what you're going to hear is this.
I think the
What's that?
I think Zoom's noise reduction feature might have removed that.
That's what I was afraid of, unfortunately. I noticed that I was playing with that the other day, and depending on how I shield a microphone, sometimes it will hear. I don't know if anybody heard CQ, but it went da 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 da, and that was done with a sort of a raspy sounding Morse code signal because it's sending a pulse width modulated signal to the speaker. I apologize if it didn't come across. I really hate Zoom for doing that noise suppression. I know that WB2U and I went through this when we were trying to do some CW a long time ago with Zoom, but you'll be able to see that on the later on with the document as I send it up on the website. Okay, so going one going back to that again, this is fine. We can do this, but you can see that this is going to be extremely tiring to write out messages using this particular routine. You know, if I have to type everything in like this for every single thing I do, I'm going to go absolutely crazy. So the question is, how do I get around that? How do I make this a lot more compact? The way to do that is with what are called libraries. And sure enough, someone has written the Morse.h library. And the Morse.h library basically does exactly what we did on the previous page for every single letter of the alphabet, every single character that you could generate with Morse code, with all the proper delays, all the interface to a pin. And the pin can be either you can send either a 1 or a 0 to that routine. And if you send a 1, it'll send a beep. If you send a 0, it'll do a push to talk. So this makes it allows you to do Morse code automatic keyers, for example, by sending push to talk signals to your keying routine or your keying hardware. So again, what we do here, in order to include a library, and again, these fellows, Eric and Mark, put this together a few years back. I put a pound include, and I type the name of the header file associated with the C code that's in that library. It's always good when you set up a library call that you write where the heck you got it, because if you put something down here, like Morse.h, and you don't say where you've gotten it from, there may be 6 versions of Morse.h out there. People are just too lazy to write Morse 111.h or whatever, and you might find that you've included the wrong library command and your program won't work. So it's always a good idea to put the URL where you can download that specific library command. And I'll show how you add libraries later to the Arduino IDE. Okay, so now in this case, we're going to again set the speaker pin to 9. We'll set the constant words per minute to 20. But unlike before, I don't have to calculate anything. The Morse.h routines all do that. So now all I have to do is create a Morse function or a Morse entity, and this is called instantiation in C++. So what I do is I create a Morse data structure by typing the capital word Morse, which is inside this routine, and I send it 3 parameters. I send it the speaker pin, I send it the words per minute, and I send it either a 1 or a 0. If I send it a 1, it sends a beep. If I send it a 0, it triggers that output to be either high or low. Inside setup, I set the pin mode of the speaker pin to be an output, which I have to do. And now you can see how simple this is. If I want to do the same thing I did before with all that multiple lines of code, now all I have to do is type morse.send message, quote, CQ, CQ, et cetera, and I have that going. So I then delay 1000 milliseconds and send it over and over again. I'm not going to play this because it looks like we have a problem with playing it. This is the only one I have, which is got some audio to it, so it's not going to be a big loss. But it plays exactly what you should have heard last time. So again, a couple things to be looked for. One is you want to look for a library which can do a lot of the functions you call. This makes the Arduino extremely powerful. You might ask, if you look at the Arduino real carefully, you look at the C328P microcontroller real carefully, it's not a really powerful machine. It does certain things very well, but it's not powerful at all. It's not going to do real-time FFTs, for example. We'll talk about how you can do that a little bit later with a little souped-up version of it. But it's not going to do a lot of signal processing for you. It's going to be basically a controller. But the advantage of the Arduino, and the important thing that these guys developed in creating a chipset and a board set, I should say, which has all these parts on it and all ready to go, is that people have written literally thousands and thousands of libraries for the Arduino. If you want to control a temperature sensor, if you want to find out what the humidity is, if you want to control a laser radar, if you want to control, et cetera, people have written code for that. And so you don't have to rack your brain trying to write C++ code. You can just download that library, and usually there are example codes for each one. I'll show you an example code a little later for a library that controls a liquid crystal display. So again, Morse was a data structure or an instantiation of this Morse, basically is a Morse structure, and the individual function calls in C++ are done with a dot command. So for example, Morse dot send message looks inside the Morse data structure for the function send message, and then it executes this command or this sending function by sending it this parameter string. Same thing true with here, Morse dot, let's see, where's the other one? I guess I don't have another one here. I'll show it in another one. But essentially, that data structure has inside it not just data, but also function calls, and send message is one of them. So this makes that 50 lines of code really down into maybe 2 or 3. Okay, so how do we add a library? Well, inside the Arduino IDE, there is in the menu item under Sketch, there is a include library command, and there is a call to manage libraries. When I click on manage libraries, I'll end up with this particular dialog box. And in this dialog box, I can type in something I'm interested in. For example, I want to create a Arduino interface to a frequency synthesized chip, the SI5351. Well, I type in SI5351, and I can see there are several different versions of what people have written. Adafruit is one of the better ones out there, and that's what I use for my programming. But the Adafruit SI5351 library can be installed by selecting the version, hitting install. Now, I've already installed it, so it shows as update here, but normally it would just, this install would become bright. You'd click on install, and it installs it into a subdirectory on your hard drive, where it has all the individual library calls. So if you look inside here, you'll see the libraries that have been already installed. These are the ones that are associated with the Arduino directly. And if you look in here, you'll see things such as wire and Wi-Fi. Wire has to do with serial interface and things like that. There's SD cards, there's liquid crystal displays, keyboard interfaces, Ethernet interfaces, a lot of different things, the EEPROM interface. And then there's some contributed libraries from different people. That's where this SI5351 library would appear. Unfortunately, I didn't scroll all the way down here, but you get the idea. All those libraries I've added show up in this list here. And I could add my own libraries that I create myself as well. Okay, I keep pressing the wrong one. There we go. Okay, so let me look at another library command and something else you can do. I mentioned before that the one thing nice about the Arduino is that it can interface with lots and lots of different things. We've showed how it can interface with a simple speaker. We showed how it can interface with a simple LED. Well, that's interesting. There's certain things you can do with it. You know, you can create your own Morse code practice oscillator with basically 3 pieces of wire and a speaker and an Arduino and a USB port, and you're up and running. You can control various on-off switches with the Arduino very easily. But let's say I want to control something a little bit more elaborate. I want to be able to display something on a liquid crystal display. And I want to, in this case, let's say we want to display temperature and humidity. So here's a little module. I think it was $1.25, amazingly cheap. And on it is a temperature and humidity sensor chip. This is a liquid crystal display. It's an organic LED liquid crystal display. And these are both going to be connected through a very simple serial interface to the Arduino. It's called an I2C bus with this integrated circuit bus. and it's one of the simplest buses out there. It allows you to control multiple devices with essentially 2 wires, and also +5 and ground as well. That has to be provided as well. But essentially, you're talking to external peripheral devices with 2 wires. So what we're going to do is we're going to talk to it with a temperature and I said humidity. I misspoke. It should really temperature and pressure. And I'm going to set up a library call. So the first thing I'm going to do is I'm going to look in my library list of library commands, and I'm going to look for that MPL 115A2 chip. As you can see, that's the chip right here. And sure enough, Adafruit has the library, so I include that. I included the library for the SSD 1306 liquid crystal display. And I have a few function calls that relate to the liquid crystal display. That tells me how wide it is and how tall it is. And then I have a couple what are called instantiations of those. I have to create a display display data structure and a temperature pressure data structure. So my display data structure, I'm going to call display, which that you see here. And then my temperature pressure sensor data structure, I'm going to just call MPL 115A2. Now, when I create the display data structure, I have to pass to it, and this is all inside the documentation that comes when you download a library. The library comes with instructions, it comes with example code, so you can, to your heart's content, try different things out. But the data structure provides the screen width, the screen height. It sets a pointer to what's called a wire interface, which is are the 2 pins that on the Arduino are A4 and A5. And then it sets the reset pin, which turns out we don't really need. I'm going to also write some stuff to the screen. Remember before we had a display command, and the display wrote to that white screen that the Arduino IDE had built in. Well, we can also write to external devices. And here we're going to write to this display data structure, this display or this guy right here, which is display. And what I'm going to do is first I'm going to clear it. Then I'm going to set the text size. These are all function calls that are inside that display data structure. Remember, this is C++, so you have the data structure name, and then you have all the function calls following the period. So this clear display clears the display out. I set the text size to 1, which is small display size. I set the text color to white. Turns out this thing will print in 2 different colors. And then I do a few little magic things here to set the display, basically to center the text in the display. So I look at the size of the text, and I divide by 2 and set it to the center of the display. But basically I set the cursor of the display to some point at XY coordinates. And then I write at that point, which is display print. Remember, we did a display print or print.println. Remember, we did that when I'm sorry, let me restate that. Serial.println when we were talking to the serial port. Here we do a display.println, and that prints directly to the liquid crystal display. And then to display everything, I have to type one more thing, display.display. Okay, so one more thing I want to set up inside my initial call. I have to turn on my humidity, or excuse me, I keep calling it humidity sensor, but my temperature and pressure sensor. To do that, I run this command, display.begin, and that is the this is the liquid crystal display. I misspoke again. I want to set that up first. So I define the I2C address for that display. There are 2 I2C addresses that are available on these LED displays, and they're addressable by changing a little jumper on the back of the screen. But it comes default to octal 3 Charlie. And so I set that to octal 3 Charlie. That's the display's address for I2C. And then I set the temperature pressure sensor to begin. So that sets up the voltages on the sensor for displaying temperature. I also set up a serial interface so I can debug it. Remember, serial.begin allows me to write data to the serial debugging screen. And then I run my routine splash, which displays my welcome to the world of the Arduino microcontroller. And the loop, all the loop does is sets up the, let's see here, this is the main command, serial, excuse me, the get pressure command. So I get the pressure by reading from the MPL 11582 using the get pressure function. The temperature I get by using the get temperature function, and the display I just set the display. So long-winded way, and I apologize, this sounds more complicated than it really is. There are really two libraries involved here, and really in a sense, three libraries, because there's also the serial display library, which is embedded in the IDE. But the external libraries are the ones for the Adafruit temperature pressure sensor, which is this guy here. Temperature pressure is done through this serial interface going to the IDE, to the interface, to the Arduino. And then there's the liquid crystal display, which is also talking to the exact same pins. Now the question is, how come they don't interfere with each other? Well, they don't interfere because they have two separate octal addresses. So what happens is the Arduino sends, hey, I want to talk to octal 40, and the unit that responds is the temperature pressure sensor. I want to talk to octal 3 Charlie, well, then the LED responds. Note the problem though, if I use I2C, I can't have multiple LED displays, or I can't have multiple temperature pressure sensors if they have the exact same octal address, because they will conflict with each other. And this has gotten around with what's called the SPI interface, we'll talk about a little bit later. But it's a very simple data structure that is created with this serial interface, the I2C, that talks to the outside world. So let me now just play this, and you'll see down below, the very first thing that happens is my display shows up, and the next thing that happens is I get the pressure from my little sensor here, which is connected with 4 pins. It's connected 2 pins to the I2C interface, which are the orange pins and the green pins. And then the yellow pin and the red pin are connected to +5 and ground. So again, the interface, first of all, clears the display, and then it reads the external sensor for temperature and pressure, displays it, gets the both of those commands, and then it does a refresh of the screen and does it all over again. Notice that it doesn't constantly repeat the welcome screen, because the welcome screen was only done inside the setup command. Notice that splash is only done once here. It's not done inside the loop. If I put splash inside the loop, then every time I'd read a temperature and humidity, I keep calling humidity, temperature and pressure reading, it would repeat the welcome screen, which I don't want to do. So this allows you to set up some initial parameters, initial welcome screens, initial displays on, what the version of your software is, et cetera, and then you can wait so many seconds and have that disappear, and then the program starts from there. Okay, so we've been using in this last screen this I2C interface, and the advantage of the I2C interface is that it's super simple. It just requires 2 lines and power and ground. And it uses what's called an open collector bus. So it can actually operate with either 3.3 or 5 volt logic, which is very, very nice, because there are devices out there that will not tolerate 5 volts. And I can use multiple masters. I can't use multiple slaves because remember that it's looking for a specific address, so I'll be writing to the same thing in multiple locations. The SPI, which is a serial peripheral interface, we'll talk about a little bit later, but that's a little bit simpler protocol. But it also allows multiple devices of the same kind to be connected together, because it allows the use of that reset line. Remember, there was a reset line that I said, we're going to ignore. Well, that's where that comes in handy. I can reset the device to be ready for the SPI interface. It's also much faster. Okay, so Arduino libraries, we talked about loading them in and examples. One thing nice about the Arduino libraries is that as soon as you load a library, you will get a entry here in your examples, which has a bunch of different possible examples that you can run. It also provides you all the source code. So all your source code will be downloaded as well. And that will be in that directory that's associated with your Arduino libraries. So I strongly recommend when you load a library that you look at the source code and give examples. Well, here's a good example. Remember, I used the liquid crystal display to display welcome to Arduino, et cetera, and display. Well, it can do lots of other things. And here are some examples. As you can see, it can do some fairly sophisticated drawing, not super fast. It's not going to do waterfall displays on one of these OLED devices, but it certainly can do things like S-meter readings. It can do things like generating sliding bars to show you, whether something is on or off. Lots of interesting graphics. This library, which is right down here that I just loaded this example code from, allows me to essentially do all these things from this single Arduino interface. And by looking at the code, I can cut and paste example code into my application and use it to do whatever I like. So it's a super nice interface. And like I said, there are hundreds and hundreds, actually thousands and thousands of libraries now available for the Arduino. Okay, so we've talked a little bit about how the Arduino works, how we can program it, and there are a bunch of different types of Arduinos. The Arduino Nano comes in lots of different flavors now. The simple Nano that I just illustrated there they're still available, but they're trying to push more and more of these more sophisticated ones. A lot of them now allow you to use Bluetooth low energy connectivity in addition to USB. Some of them have Wi-Fi interfacing. So this one, for example, uses Wi-Fi, crypto chips on it, so for data protection. There are little tiny ones that are 5 grams that can be used for wearable applications. So you can put this inside of a small badge on your chest and use that for some display. There are also ones that include multiple different sensors, accelerometers, gyroscopes, proximity sensors, motion sensors, temperature sensors, audio microphones. Here's one with a little microphone built in. So the tremendous number of different flavors of these Arduinos are now available. They vary in price. You can get them from as low as a few bucks, $10 here, to $25, $30. And like I said, some of the Chinese clones, I don't always enjoy buying from overseas, but at $4 a pop, if you can buy a bunch of them and they work, I'm pretty happy with those, and they're useful for playing around with. Now, what is the problem with the Arduino is that like I said, it's not a super fast processor. However, there are processors out there. For example, this little teensy, oops, I'm sorry, drawing all over myself here. This little teensy, which is very low cost, about 20 bucks. And look at the speed, 600 megahertz. And it actually could be clocked to over 1 gigahertz clocking rate. It's absolutely amazing. It's the fastest microcontroller that's currently available. 20 bucks. It's a little bit smaller than the Arduino Nano. And I'm seeing more and more folks build with this for doing things like real-time spectrum displays, real-time waterfall displays. The other thing that's nice about this particular chip is that there are what are called daughter boards or top hats or hats for these things. If you're familiar with that, where these pins, for example, that are along the side will actually support a superstructure of another chip or board that's on top that contains more integrated circuitry. So for example, I can put an audio hat on top of this, and here's that audio hat here, which allows me to do full stereo audio, as well as being able to send that audio streaming through DMA to direct memory access to the chip here, which allows me to do real-time fast Fourier transforms. So for example, if I want to do a spectral display, an audio spectral display, this can be done in real time while the processor is doing other things on the side. So it's absolutely a phenomenal chip for 20 bucks. The advantage of this particular Teensy is that it can be programmed directly using the same Arduino IDE. There's a slight update for it. It's a slight interface change that allows you to access the Teensy, but it's really trivial. And it just, what that does is allow the Teensy to show up in the list of microcontrollers in the list of programming interfaces that you have. So again, there's no need to be constrained by the lower speed. If you really want to do some high speed processing, the Teensy is a really nice way to go. I wanted to give you a list. I'm not going to go through all these individual interfaces, but there's some really neat projects out there. Some of these, I hope you get a chance to take a look at. SWR meters. Remember that we've got A to D converters on side the chip. So for example, if you can measure the forward voltage and the reverse voltage, which can be done with a very simple SWR bridge, then you can use the Arduino to sample that, use the Arduino to compute the SWR from it. I can interface a GPS to the Arduino. I can use it for beacon transmitters. I can use it for things like antenna rotor control. There's some really interesting things for satellite control. Rig control, cat control. I can mimic the cat control on Yaesu and ICOM rigs. Antenna tuners, I can build an automatic antenna tuner using the Arduino to control the switching of capacitors or inductors in series or not, or in parallel or not, depending upon what the SWR was. I have an article in December 2020 that shows using the Arduino in a synthesized QRP transmitter design. And in fact, here it is. This is the synthesizer portion of that particular article. And if you notice, it's got a Arduino Nano that's sitting here on the circuit board. It's got an SI5351 synthesizer chip. And it's got, I think, one resistor, one capacitor, I think two capacitors actually, and a voltage regulator. And that's the whole thing. Everything else is controlled by software. It allows me to talk to a liquid crystal display, just like we did before. And here is a rotary encoder display, which I use to interface to the Arduino. And this provides me with full 80 through 10 meter coverage, including 60 meter channels in 10 hertz steps. I'm getting plus or minus 5 hertz frequency accuracy once it's calibrated. And it's kind of an interesting little device that can replace a crystal oscillator inside a QRP rig, or you can use it as the foundation for a whisper transmitter or anything else you'd like to build. Some sources. You notice that most of the stuff that I did for my example programs were done on a little board like this. You can get these breadboards from lots of sources. eBay, Adafruit has them, lots of places, DigiKey, Mouser. These are really nice to have. These come in bunches like this from Adafruit. You can tear them apart for individual connections. You can tear them in groups of 4 or 8 or 6 if you want to make serial interfaces out of them. Really nice. This little device here is only $1 or so. It's a converter which allows you to take a USB connection and convert it to 3.3 and 5 volts to use on your breadboard. The Arduinos themselves, you can get them from lots of sources. The Micro Center in Rockville has them. If you got to go all the way to the back, if you've been in a Micro Center store in Rockville, go all the way to the back. Right-hand side, you'll see all the Arduino stuff on the shelves there. Lots of interesting sensors that they've got. Arduino Unos, Megas, Arduino Nanos are also typically available there. Some of the BLE stuff, the Bluetooth low energy, are not yet available, but I think you can get them through their online source. some of the eBay sources, you can get Arduino Nanos for in the. I used to get them for like $2 a piece. Now they've learned that people are buying them. Now they're massive $4 a piece, so not very expensive. Breadboards, like I said, these are very inexpensive, about $5 or $6 a piece. And Arduino modules, there are literally hundreds and hundreds of those available. Books. I've got several that I highly recommend. The one that I highly recommend is the one by Jack Purdom. This is the microcontroller projects book. And the second one I really also like is the Arduino for ham radio, which is this book here, and that's by Glenn Popiel. KW5GP. Both of those are excellent books, and they give you lots and lots of programming examples, rationale for how they do that. One thing I like about Jack's book is it goes into a little bit description of C and C++, you know, what's important to know, what you don't need to know. The thing that interesting about Jack, which I didn't realize, that Jack was very active in C programming many years ago. One of the very first books I ever got in C was a book that I was really the Bible of C programming language. Turns out Jack wrote it. I had no idea until I came across this book, and then suddenly it dawned on me that Jack had written that. So very, very good writer, and some really interesting projects. For those of you that like to play around with other than ham radio stuff, you want to build a robot or whatever, there are a couple really neat books as well, Arduino project handbooks, lots and lots of good examples. And some of those you can turn in some really interesting ham radio stuff as well. Probably the most important source for you in terms of looking at what you have to write inside your scripting language is can be found here. The Arduino language reference, which is on the arduino.cc website, contains a list of all the different commands that are built into the Arduino programming language. And if you look at those, you'll get lots and lots of examples of how that's done. And also there's another source of Arduino projects, create.arduino.cc project hub has, again, lots and lots of examples. You are not alone with the Arduino. That's one reason I particularly like this microcontroller. There are better microcontrollers out there. There are faster microcontrollers. There are things like PICs and what have you. But I tell you, if you want to have a wealth of already written code that you can cut and paste from and learn from, it's hard to beat the Arduino. The guys who wrote this as an open source architecture, it was a brilliant stroke of genius, and getting lots and lots of people involved in using this really powerful microcontroller in lots and lots of fun projects. So thank you very much. I want to just point out that a PDF copy of the presentation can be downloaded on the website there, just mycallsign.com. It won't contain the audio files, but I'll try to upload those just so you can hear what the CW sounds like. I apologize for the Arduino. I apologize for Zoom truncating the Arduino in terms of the sound, but c'est la vie, as they say. Thank you very much. I think with that, we can maybe open up for questions.
Okay, well, thanks, Bob. That's awesome. What a great presentation. So questions? Come now.
Sorry for my lights going out on me. That's where my Arduino controller is needed to turn that light on and off.
Yeah, so go ahead, Alyssa.
That was an accident. Sorry about that.
Oh, okay.
Thank you.
All right, so we have any questions?
There's a lot to be covered, unfortunately, and it's hard to do that in a short presentation. But I wanted to get everybody started in realizing that it's not difficult to get started with this. You know, one little breadboard, 3 chunks of wire, and an LED, and you're up and running. So give it a try. I think you'll have a lot of fun with it.
Okay, great. Well, thank you so much.
You're very welcome. Thank you.
Thank you very much.